So we have this ion, PCl4 minus. And we need to figure out the central atom. We need to figure out how many electron groups around the central atom. And we need to name the electron groups, or the shape of the electron groups. So what do we do first? What would you guys do? Okay, draw the Lewis structure. So what would we start with, Sienna? Okay, how many electrons? So let's start with phosphorus. How many valence electrons does phosphorus have?
5.
Okay, well, we've got one of those. And then chlorine, how many valence electrons does chlorine have?
7.
Okay, thanks. So 7, and there's 4 of those. So that gives us 28. And then this minus charge gives us 1 more. So we'll just put a 1 over there. Okay, then we add this up. And so this should give us 34 valence electrons that we need to show in our Lewis structure. All right, so now we know how many electrons. What else do we do? What's next? So we have these atoms we need to put in the structure. Yeah.
Then you can find the essential atom, which is phosphorus.
Okay, good. So put phosphorus in there. And how did you decide on phosphorus?
Because there's 4 chlorines and those are 2 arranged around evenly.
Okay, let's do that now. Let's put them around the phosphorus, spread them out. Okay, so now how many electrons have we shown? Good. So there's 2 per bond, so 2, 4, 6, 8 that we've shown. So now we're down to 26 electrons. Where should we put these electrons? We've taken care of all the atoms. We need to fill the electrons up now. Where should we start putting these?
Around the chlorines.
Good, around the, not the central atom, we want to start on the surrounding atoms. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now we've used up 24 more electrons. We have 2 left. Where are we going to put these 2 electrons? 2 left over. On the phosphorus. Good. So phosphorus is in that 3rd row, so it can hold more than an octet. Okay, so now how many electron groups are around our central atom? 5. Good. So 1, 2, 3, 4, 5. Good. So let's put 5. And then if we have a central atom with 5 electron groups around it, what do we call that shape? Good. Yes, good. That's it. Trigonal bipyramidal. Okay, luckily this one's a drop-down question, so you don't have to spell it. Okay, so these things are. Alex has this nice in the explanation. It has this nice diagram. So I think I can remember linear. I think I can remember trigonal planar. If it has 3 groups, it's trigonal planar. We've been talking about tetrahedral a lot, and I think I can remember tetrahedral. Trigonal bipyramidal is something that I have a hard time remembering. So this might be something that I put on my note card. That 5 electron groups around the central atom, that's a trigonal pyramidal molecule. Okay. I have not seen any examples that have octahedral. Has that come up in your homework ever? Do you remember? Okay. So I think this is the one that I would put on my note card. If any of these are hard for you, I might put these on your note card. So we did this review question today because I went back through the final and I looked at our chapter exams. And I wrote down how many people missed each type of question on the chapter exam. And 77% of us missed this question. So not all of us, but a lot of us missed this question. So this would be one that I would review. And I would also probably put something on my note card about this one. Okay. Questions on that? Was that helpful? Okay. All right. Let's look at our schedule really fast. So there's some things that we don't want to forget. We're getting close to the end. We still have that signature assignment. It's only worth 10 points. It's just like a regular, it's in the assignment category. So as soon as you get that done, go ahead and turn it in and just get it out of the way. I think May is going to get really busy. So try to get that out of the way as soon as you can. As soon as you're done with Lab 34, go ahead and turn in your lab book so that you don't get a fine. Next Tuesday is the last day you can turn in Lab 34, and that's also when Alex Chapter 13 is due. Okay, so next time we're going to review Chapter 13, then on next Thursday we'll have the Chapter 13 test. That's the last chapter test. And remember, that's the last test that goes into the 65% to pass. So if you're trying to work on your 65% exam score, this is the last test to bring that up. Okay, and then the next 3 days will be the final review. So this next week after the second week of May, and then we have our final, and then we're done. Okay, so it's gonna go pretty fast. Okay, all right. Questions about the final or about the end? Okay. One more reminder. I'm gonna try to remind you. If you're a senior, they're going to try to start collecting your Chromebook before we've taken the final. Don't give them your Chromebook until you've taken the final. I've gotten permission from the principal to do that. So don't give them your Chromebook until you've taken the final. Okay, I think that's it. Okay, let's go ahead and look at our last slide. So we have just a few things to cover. So last time we talked about isomers. We talked about constitutional isomers, where we have the same formula, but they have a different connectivity. So we looked at propene with a bromine connected to the middle carbon, and we looked at propene with bromine connected to the end carbon. So that's a constitutional isomer because the atoms are connected differently. A bromine is connected on the end versus in the middle. Today we're also going to talk about this different type of isomer called a stereoisomer. So they only differ in the 3D arrangement of the atoms. They have the same formulas. They have the same connectivity. So we have here, if we are looking at these two stereoisomers, we have a carbon connected to a carbon, connected to a carbon, connected to a carbon, and the double bond is in the middle. Oops, I'm going the wrong way. There we go. Here we have a carbon connected to a carbon, connected to a carbon, connected to a carbon. The double bond is in the middle. But remember last time we talked about how if we have a double bond, the groups cannot rotate around a double bond. So the carbon group up here is locked. So if we cut this double bond in half, this carbon group is locked above the double bond, and this carbon group is locked above the double bond. If we look at this molecule and we cut it through the double bond, there's a carbon group above the double bond, and there's one locked below. Everything else about these molecules is the same, but they are called stereoisomers. They have different chemical properties, they have different physical properties, they are different molecules, but the only thing that's different is that these carbon molecules are locked on the same side, and these carbon molecules are locked on different sides of the double bond. Okay, so that's a stereoisomer. So the only difference is the geometric arrangement of the molecules. Okay, so we're going to call them cis or trans. So if the two groups, the two carbon groups are locked on the same side, that's called cis. If the two carbon molecules are locked on opposite sides of that double bond, this is called a trans conformation. So you have to be able to recognize that. And it's kind of easy to recognize them in this form. It's a little bit trickier if it's a line structure. So just make sure you familiarize yourself with what it looks like. So really quick, let's draw what this looks like if it's a line structure. I'm not sure if this will help, but so this one would look like we have a carbon group, then we have a carbon group, and then we have a carbon group, and we have a carbon group. Oh, I deleted that one. Don't delete it. Okay, and then our double bond is down here. So we have two carbon groups on the same side. That's a cis molecule, and this is the same. It's 2-butene, but if we just draw it like our regular we've been doing, this is trans. We have, if we cut it through the double bond, there's a carbon group above it and a carbon group below that. Okay. All right, so I just wanted to pull in, have you guys heard of oleic acid? This comes up in like either nutrition or like biology sometimes. This is a pretty common cis molecule. So if we cut the molecule through the double bond, the biggest groups are on the same side of the cis conformation of this molecule. Okay, and then here's an example of a trans molecule. So we can see if we have that double bond and the carbon groups are on the same side of, locked into place on the same side of that double bond, then it's going to cause the molecule to be bent. If it's a trans conformation, then we have more of a linear structure. Okay. This is pretty interesting. Trans fats, our body has a hard time breaking these down. So these are more stable than a cis conformation. So that's why trans fats are kind of regulated. They're not as good for us because that bond conformation is harder for our body to break down. So just the carbons being on the same side or on the opposite side can change the reactivity and the properties of the molecules. All right, so go ahead and try to practice this. Try to draw these two different conformations. So these are isomers. They're the same. They have the same formula. They have the same atoms connected to each other. The only thing that's different is their 3D space, the way they are arranged in 3D space. All right, once you've drawn that, take another minute to draw it, but once you've drawn it, check with someone around you. See if you drew it the same way that they did. How did that go? Okay. Everyone okay? All right. So how about this one? So I like to look at this end. Okay, so I know that I'm starting with pentene on both of these. And then this tells me the conformation, and this tells me what other groups are attached to it. So I would start with the pentene. 1, 2, 3, 4, 5. And then it's 2 pentene. So I could either start from 1, 2 or 1, 2, it doesn't matter. So I'm going to start over here. 1, 2, 2 pentene, and then 4 methyl. So 1, 2, 3, 4. And so I'm going to draw my methyl group up. I don't know what it's doing. All right, so then I need to check and make sure that it's the correct conformation. So I'm going to draw a line through the double bond, and then I look. Is there a carbon group on one side and on the other side? Yes, good. Okay, so then this is the same isomer. So I'm just going to take, oops, my methyl group disappeared. I'm going to take one of these pieces. So what I'm going to do is I'm going to take this methyl group, and I'm going to flip the methyl group up. And that'll give me the cis conformation. So I'm going to put this here. So it'll go here, and then I'll have my double bond, and then the rest of the molecule. So now when I draw a line through the double bond, I have a carbon above. I have both of my large carbon groups above the double bond. So this is a cis. They're on the same side. This is a trans isomer. It's on opposite sides. If we counted this, they would have the same carbon molecules and the same hydrogen molecules. Okay, all we did was we just flipped that methyl group to the same side. Okay, questions on that? You guys think that you could do that? Okay, all right, good. Okay, so this is our last, we have 2 topics. This is our last 2 topics that we're going to talk about. So we're going to talk about 2 reactions of alkenes. So we're going to talk about addition reactions. So we have a double bond, an alkene. We add another molecule, and that molecule adds across the double bond. So what's happening here is we have 4 electrons shared between the carbons in this double bond. So 2 for each carbon. And the double bond gets broken, and we have an electron here. So these bonds just kind of shift to the sides. And this double bond gets broken, and this carbon, this was a bond, and it got broken. And then whatever's here, we have X. I don't know why I'm doing that. We have an X that comes in and a Y that comes in with its electron. And now we get new bonds formed. So we're just adding something across the double bond. That's why it's called an addition reaction. So we're breaking 2 single bonds. We're breaking this bond here, and we're breaking this bond here. And then we're adding 2 new single bonds. So this is now bonded to a carbon. This is now bonded to a carbon instead of each other. So there's a whole bunch of different types of alkene additions. If you took a full year-long course of organic chemistry, you would go into detail about the mechanism, how each of these work, how they add. But we are just going to focus on 2. We're going to talk about hydration and hydrogenation. But just know that there's many, many more types of reactions that could happen at a double bond. So hydrogenation, if we look at this word, what do you guys see? Good, we've got hydro. We also, if we go all the way over, we've got hydrogen. So hydrogen, we're adding hydrogen to the double bond. So we start with an alkene. Somewhere in our molecule we have a double bond. Then we're going to add hydrogen with a catalyst that makes it go faster. And then hydrogen adds across this double bond, and we end up with an alkane. We get rid of that double bond. And this picture is on your chapter 13 notes. Have you guys heard of hydrogenated vegetable oil? So this is what they're doing. Somewhere in that molecule, there's a double bond. They're adding hydrogen across the double bond. And then now it has either no double bonds or less double bonds. So double bonds can spoil foods because they're pretty reactive. So over time, they can go rancid. And so that helps things like margarine stay good for longer. Okay, so some key things for hydrogenation, you have to have a catalyst. A pretty common catalyst is palladium. So what they do is they put palladium in a carbon powder stuff. So that's called palladium on carbon. And then you add in a pressure vessel, you add a whole bunch of hydrogen, you have your catalyst, and then you heat it up usually, and then after some time, your reaction is done. So that's a pretty common catalyst, palladium on carbon. You could also see a nickel catalyst or a platinum catalyst. These metals are really good at helping the hydrogen break its bond, and then those hydrogen atoms can add to your double bond. A key that's going to be important for your Alex topics is that for every double bond, you need one hydrogen molecule. So one hydrogen molecule for every double bond. And I think that's pretty clear from the picture on your handout. But just make sure that, I just want to make sure that you knew that. So one double bond requires one molecule of hydrogen. All right, questions, thoughts, or concerns? Okay. So I haven't seen this, but as it's asking you to figure out if a reaction will occur, if it doesn't have a catalyst, then this reaction probably won't happen. So if you had a reaction and it doesn't have a metal catalyst, then this is not going to happen. I haven't seen that happen. I have not had it where there's no reaction is the correct answer. But just keep that in mind. If you don't have a metal catalyst or you don't have enough hydrogen, then this is not going to work. Okay, so let's look at these two different molecules. The hydrogenation of these two different molecules. How many molecules of hydrogen would I need to hydrogenate this molecule? Good, 2. And how do you know that?
Because there's 2.
Good, there's 2 double bonds. So I would need 2 molecules of hydrogen to fully hydrogenate this molecule. Good. And then I thought this was a good example because we have two double bonds. These are really close double bonds. And then we have other double bonds that are not close together. So these are different molecules. But if we hydrogenate them, we will end up with the same molecule. So this is a 7-carbon chain, so we would end up with heptane. So I think that's kind of interesting. We can start with different molecules, do the same reaction, and get the same product.
Not like super hardcore.
Okay, the last reaction that we're going to talk about is alkene hydration. So be careful, they do look really similar. Hydrogen is the whole hydrogen name is in the last type of reaction, hydrogenation. So hydration is when we're adding a water across the double bond. So we have our double bond, we have water, and then for this reaction to go, we also need a catalyst. We need an acid catalyst. So this is called an acid catalyzed reaction because we need that acid for this reaction to happen. So usually you're going to see H plus above the arrow, or you could see sulfuric acid or phosphoric acid. Okay, so again, one of these hydrogen-oxygen bonds breaks, one of these double bonds break, and then we form two new bonds. We get a hydrogen-carbon bond, and we get an oxygen-carbon bond. For this molecule, it doesn't matter. We started with ethylene. We got ethanol. If I put the hydrogen over here and the OH over there, it's the same molecule. If I flipped it, it's the same, okay? So for this symmetrical molecule, it doesn't matter where I put the hydrogen and where I put the hydroxide. But it does in unsymmetrical molecules. So this is our symmetrical molecule. It doesn't matter where the hydrogen and oxygen go. But if I have a molecule that's not symmetrical, where I have like a double bond on one side of the molecule. So this is propene. I have 3 carbons. I have a double bond between the first and second carbon. If I look at this carbon, the end carbon only has 2 hydrogens connected to it. The second carbon has a carbon connected to it, it has a hydrogen connected to it, and it has this other carbon group connected to it. So this is it's called the more substituted carbon. So the rule is, what this person observed, Markovnikov observed, is that the hydroxide, the OH group is going to bond where there's a more substituted carbon. So if it already has more groups, the OH group is going to go there. Okay, and that has to do with the mechanism of how this works. So if you're interested in learning more about what is actually going on, where are the electrons moving, then you would learn that in organic chemistry. That's something that we talked more about in organic chemistry. We're not going to talk about that. But yeah, so this carbon is going to get the OH group, and then the less substituted carbon is going to just get the hydrogen. Okay. All right, so go ahead and see if you can predict the product of this hydration reaction. So we're adding water across the double bond. Where will the water go? All right, where do you guys think? Where will we end up with a hydroxide group? So we're gonna get pretty much the same molecule. We're gonna get this cyclohexane. And we still have the methyl. The methyl didn't go anywhere. And we have to put an OH group. So this is gonna break into an OH. And it's going to break into a hydrogen. So where will the hydroxide group go? So we're looking at these two carbons, this carbon and this carbon. It has to add to a carbon that participated in the double bond. So it can either go here or here. And we know from Markovnikov's experiments, from his rule, OH goes to the more substituted carbon. So which carbon is more substituted?
CH3.
The one with the CH3. So we're going to get the hydroxide right here. Oops, let's see if the board will let us write. And the hydrogen just goes here, but we don't have to draw it. So I can write it in there. So that would be the other hydrogen. Or not the other hydrogen. This hydrogen adds here, and our hydroxide adds to the more substituted carbon. And again, in a line structure, we're not going to draw that hydrogen. We don't show hydrogens. Okay, let's try one more. This is backwards. We need the product. What product, or excuse me, we need the reactant. Which reactant would give us this product? Okay, let's talk about this one. What do you think we need up here in our molecule?
Hexene.
Okay, hexene. Okay. And what number of hexenes? Let me draw hexene. 1, 2, 3, 4, 5, 6. And that's 1, 2, 3, 4, 5, 6. So that matches. Okay, don't forget we also have this methyl group. And then where would you put the double bond?
Like, where's
Do you want to put it up here?
I mean, it's probably not right, but
That's okay.
okay, sure. Would it be like? Could it go here?
Yeah.
Or, okay.
Oh, use the other end.
Oh,
It
sorry.
doesn't. It just doesn't work very well. I see where you're.
Yeah, that's where.
Perfect. Sorry, the board is kind of annoying. Okay, there we go. All right. Anyone else come up with something else? Yeah.
I did the same thing, just put it on the other end.
On the other end? Yep, good. I would still put, so this would also work. Hexane, and put the double bond over here. Good. So we can't say for sure what we started with, but these are two options. Let me draw this one up and see what do you guys think about this one? 1, 4, 1, 2, 3, 4, 5, 6. What if this is our double bond?
Wait, so does the extra hydrogen go on the substitution?
The extra.
On the H2O, because the OH goes on the one.
Yes, we just don't draw that hydrogen because it's a line structure. If you're drawing the condensed structure, you would need to show that hydrogen.
And it'd just be on that substitution there.
It would be, so depending on where our double bond started, the hydrogen could end up here, or the hydrogen could end up here or here.
Oh, okay.
Yeah, good. Yes, so so one side of the double bond gets the OH, whatever other side gets the H. Good. Okay, what do you guys think? Do you think that would work? Because if I'm adding OH to the more substituted side and hydrogen to the less substituted side, I would still end up with this. So lots of options for this type of question. Okay, that is our last slide. So now we've covered all of the ALEX topics. So in theory, you could be able to get 100% of your pi progress right now. And there's one student in our other class that has gotten the 100% pi progress. The average right now is 80%. So just kind of think, maybe you need to work a little bit more, or are you right on track? Okay, so just think about our pi progress is going to be due the day of your final. Okay, so I would try to have it done before then, but that's when it's going to be due. Okay, I don't know. One more thing, I don't know if I talked to you about this, but your final, you need to take your final on the final day, unless, like, if you're sick, obviously we'll figure something out. But if you have something scheduled on the 17th of May and you can't make it to take the final, you need to let me know before. I have to turn in your final grades the next day. So we need to work out something before if you're going to be gone, so let me know. Okay? All right.